Welcome everyone. In this video, we will try to understand the public key infrastructure, the blockchain network, how the blockchain function, and the stealth address. The concept stealth address comes from Monero's blockchain. Its privacy feature, like as in blockchain, every transaction in blockchain is transparent, so everyone in the blockchain network can see, monitor, analyze the transaction, like who is the sender and who is the receiver. So in order to make the receiver or sender anonymous, like we have to hide the sender or receiver. So Manuro introduced this privacy feature concept stealth address. So before that, we need to understand how public key infrastructure works, like what is public key infrastructure, how key exchanges are made, like how one is encrypting data using receiver's public key, and how receiver is using his private key to decrypt the same data. So we need to understand this, how public key infrastructure works, PKI, and the basic functionality of blockchain. So let's start. Basically this video we will covering the introduction to cryptography, what is cryptography, and public key infrastructure as I described before, what is PKI, and how PKI works in SSL TSL protocols. Now we will get to know that later. What is SSL? Basically, SSL is secret socket layer, and which is similar as TSL. Because TSL is advanced of SSL. So if you have seen any web page like before in initial part of URL, you will see the HTTPS and HTTP. If you seen the HTTP not with S, then you get the message that website is not secure. Do you want to continue? So that means that they don't have SSL certification with them. So in order to understand what is SSL, we will deep dive into that part by part. So then we will describe how hash functions work. This is the one of the main important part of encryption side, both encryption and decryption side. When we encrypt data, we convert that data into some hash format, so that when receiver matches the hash, then he will get to know that data is not tampered or something is not being mismatched with data. Then digital signature, we will see how digital signature works. Digital signature is basically using key exchange mechanism. Then we will learn more about how encryption is work. So we have taken RSA algorithm here. So we will understand how encryption through RSA perform. So then next we will see the basic structure of blockchain, how blockchain is functional in a network, how blockchain act as a network, decentralized network. We will get to know that. Then the privacy in blockchain, how blockchain is transparent, which is advantage, meanwhile also it's disadvantage too. So we will see what is privacy in blockchain. Then we will see the key components of Monero's privacy model. We will deep dive into what Monero privacy model offers to make the privacy more better. So then we will see the concept and implementation of stealth address. How using stealth address the receiver is being anonymous. We will see the complete transaction flow, like from sending to spending. We will see everything from creating transaction to broadcasting transaction to the network, and how receiver is decrypting the transaction, and how receiver is staying anonymous in the network. Then we will see the privacy implication, use cases, and benefits of stealth address. So let's start with introduction of to cryptography. So when we speak about cryptography, usually the thing come in our mind is that cryptocurrency, right? So what is cryptocurrency? How this function? What are risks involved in that? Is it legal, illegal? So we need to understand how this cryptocurrency, for example, Bitcoin, Ethereum, work in real life. So they are digital currencies, we know. So we will see how cryptography make sure that these cryptocurrencies are safe and reliable on the network. So cryptography is a study of secure communication. We often view it as science of encrypting and decrypting the information. So encrypted and decrypted information basically contains, like, when data is transmitted from one place to another, we try to encrypt the data from the sender side and decrypt the data in receiver side. So that is involves converting of readable plain text into unreadable ciphertext using project qualification, and only authorized party can further decrypt the ciphertext into plain text. So cryptography is basically categorized into two types. One is symmetric and asymmetric. So in symmetric key cryptography, we use only one shared secret key on both sides, both on receiver and sender side. That key must be kept secret to maintain the security. If the key is exposed or publicly available to everyone, then everyone can in the network or anyone can decrypt the message. The other is asymmetric cryptography, is also known as public key cryptography. Here we use both. Here, every sender and receiver is accompanied with public key and private key. So, if sender 1 is sending some data to receiver 1, then sender will use receiver's public key to encrypt the data, and receiver will use his private key to decrypt the same data. So, public key is available to anyone. So, as you know, then the private key is kept secret by the owner. Private kept key need to be kept secret by the owner. So the key, how this key are generated, basically there is this key generation function which we provide a big random number. We will see in RSA how this key generation takes place. So for now, we can consider that some big random number is given to the key generation function, and that key generation function gives us two keys, which is one is public key and private key. So this is symmetric key cryptography or symmetric key cryptography. If you can see, if we take sender as Alice and receiver as Bob. So in symmetric key cryptography, one you can see the shared secret key is used to encrypt the data plain text. Then the ciphertext is sent further to Bob, and the same secret key, shared secret key, is used to decrypt the plain text. So this is symmetric key cryptography. Then asymmetric cryptography, we can see that every sender and receiver is accompanied with having private and public key. So, for example, here Alice will use Bob's private key. Sorry, Alice will use Bob's public key to encrypt the data. So the ciphertext, and then after the ciphertext is generated, the ciphertext will be sent to the Bob, and the Bob will use his private key to decrypt the data. So this is asymmetric cryptography. How this is happening, like how Bob is able to decrypt the data using his private key, just because Alice uses his public key to decrypt the data. So we need to understand how this is happening behind the scene. So let's get to another part, how public key infrastructure works. So basically it's a framework that associate a digital certificates like SSL certificate as said before to manage public key encryption and associate digital certificates. Okay. So it ensures secure communication in network environment by providing a range of cryptographic services. So the services comes under PKI digital certificates, which are electronic documents which binds public key to an entity. For example, entity can be person, organization, or server. Includes the public key and the identity information of the owner and CA. So, in this digital certificate, which is bound to public key to an entity, has the information about the entity, for example, owner, and the CA digital signature. CA is basically central authority, the one who is monitoring all the monitors and provide all certification to any entity. For example, the example I have given before that, when we visit a secure website HTTPS, the server presents its digital certificate to your browser. So the browser checks the certificate to ensure it was issued by trusted authority. So if browser said if it is valid, then we will proceed with secure communication. Else, then risk might be associated. Still, you can able to continue to navigate to website. So the central authority part, the which is trusted entity responsible for issuing and managing DTS certificates. It binds public key to their respective entities and signs the certificate with their own private key to validate their authenticity to establish trust. So CA certificate issue the digital certificate, the SSL certificate, which is bound with their public entities public key, and then it signs the certificate. It signs the certificate using their private key to ensure the authenticity of the certificate. So then another part is registration authority. It acts as intermediary between CA certificates and client. So it is responsible for verifying the identity of applicant on behalf of CA before certificate issue. Once RA verifies the identity, it notifies CA to generate and sign the certificate. So RA is intermediary between CA and entity. So this is how certificate is provided issues in between from client to from subject to CA certificate. CA certificate authority, registration authority is intermediary in between them. So how PKI works in SSL TSL. So we discuss SSL TSL. What is SSL TSL? If we want, we can demonstrate the SSL certification. For example, if you see here, connection is secure. certificate is valid, and we can see the certificate from Google that this is the certificate ID and this is the public key of the certificate. So the organization is Google Trust Services. You can see it was issued on this time and expired on this. Which uses encryption SSH 256 SQL hash algorithm 256 encryption. We can see the details further like validity, etc. extensions, and meaning as you can see here. So this is the certificate which browser verifies and then only proceed to the navigation. So that is SSL certificate. So this certificate provide authenticity in the combination of following. Like for example, it provides the confidentiality as data is encrypting, so it is confidential. So it's remain private between exchange between two parties. It uses symmetric shared key encryption to data, encrypted data, making it unreadable to anyone who tries to intercept it. And another is integrity. It ensures the data received by client is the same what was sent by the server. So it uses message authenticate codes max to verify that data has not been tampered with. And another is authenticity. Verify that client is communicating with internet server. So during SSL handshake process, the server presents digital certificate to the client, which the client can verify to ensure it's communicating with the correct server. So as you can see, the web browser is making a request with the username John and password, my password. It goes to the server, and server responds back to its personal data to the web client. Now this is HTTP. This is insecure communication. Now when web browser sends a request to the server, it's encrypted. The site is secure and SSL certificate is provided issued to the website's web domain. So the request is encrypted on server side. Server decrypts the request and sends the encrypted response to web server, and web client itself decrypt the response sent by the server. So here there are two images you can see. This is plain TCP transmission control protocol, and this is SSL TSL over transmission control protocol. So this is insecure communication. Client make a request to server, server sends the data, and any attacker can intercept between this non-encrypted. It is plain communication. So as it is not encrypted form, both from client and server, so anyone can intercept the data in between. Whereas in SSL TSL over TCP, a secure communication line is maintained where encrypted application data is sent and request and response back to client. Request to server and response back to client. So, confidential integrity and authenticity is maintained here in SSL, TSL over TCP. So next is hash function. So why we are understanding this hash function? It is a part of encryption. We will later get to know how where hash is performing its main operation in encryption part. So basically, the hash functions are cryptographic hash functions which transform input fixed size of input into bit string. Then any change to particular fixed size, any change to any input data makes the complete change of hash. If that change is accidental or intentional, it doesn't matter. It's change the hash with high probability. So the data to be encoded are often called messages, and the hash value is sometimes called message digest or simply digest. So the hash the output given by hash function is called as digest or simply digest. Message digest or simply digest. So hash functions are essentially cryptography, provide integrity and authenticity. How integrity is maintained? For example, as you can see in the image, if I have given the input data as false and provided that input data to some cryptographic hash function, it outputs me the digest, as you can see. Now another, you can see the red fox jumps over the blue top. So I have given this input to cryptographic hash function that generates the hash digest for me. Now I have just made a very minor change here. The red fox jumps over, as you can see there is u instead of v. The rest of the input is same. Now if I provide this input to same cryptographic hash function, the resultant digest will be completely different, completely changed just because of changing one variable, one bit of input. So changing any single digit, any bit of input from input and matching the same doesn't work this way. So it keeps the integrity and authentication, like what input is being sent and hashed, we have to match the same hash with the output it generated. So this is how hash functions work. Making any changes in input, so phenomenally it changes the hash completely differently. So the example of hash, most popular hash function is SHA-256, which is secure hash function. This hash function is used in Bitcoin and Ethereum. In Ethereum blockchain network, each arc is used. So this is a very basic diagram. We provide a message m, which is arbitrary length. We give it the message to hash function, and that hash functions provide us the hash value h, which is fixed size length, fixed in length size. So another concept is here digital signature, how digital signature works. So in order to understand digital signature, we will go step by step how digital signature is been implemented, how it functions. So we are taking an example of Alice and Bob. Alice will be sender here, and the Bob will be receiver. So Alice has message M. So let's say Alice write a message, hello Bob. So hash, we have to first convert the message into hash value. So we will provide that input message to hash function, which will be h of m. For example, for sake of understanding, we will consider that the hash that has been given to the input message hello Bob is 1234. So we will try to match the 1234 and Bob's side. So another is, now the hash is generated. Now we have to encrypt the hash with Alice private key. So in digital signature, what the overall fundamental idea is that if Alice is sending some data to Bob, so in digital signature, Alice will use her private key to encrypt the data, to sign the, for example, sign the hash. So this encryption of hash is digital signature. So Bob will decrypt the sign or the verify the sign using Alice public key. So you might be thinking, what is the point here? Like anyone in the network can use Alice public key to verify the signature made by Alice. So the fact here is that anyone who is using Alice public key to verify the digital signature made by Alice in, involves the concept that Alice, the same message is being encrypted using private key of Alice. For example, if someone tampered in between network, so get to know when we match the hash after verifying after decrypting the part signature. So if the hash doesn't match, the message is been tampered. If hash match, the message will be completely untampered and it's verifiable. So it can be only decrypted using Alice public key. So the fact is that it is encrypted with Alice private key. That is saying that the message is coming from verified and valid user. So we will be encrypting the hash with Alice private key. Then we will for, let us say, S encrypt A. So A, small a is Alice private key, and the encryption part takes the two input Alice private key and hash of this. Now we will encrypting, and let us say the signature is 5678. Now the signature 5678 is unique both to message and is unique to both the message and Alice private key. Now the second step will be here sending M, which is message, and S. Alice send two things to Bob here: the actual message and the digital signature. So Bob verify the digital signature here. Now the part Bob has to perform at receiver end is that has the same message which received from Alice. This is if Bob verifies the message, hashes the message hello Bob without changing anything, he will generate the same hash which is generated by Alice. So now in decryption part, Bob then decrypts the digital signature using Alice public key A. So when he decrypt the signature, digital signature. The decryption part will take Alice's public key, and the signature, digital signature, is received from Alice. That is 5678. So it gives the hash. So it gives the hash. It will give the hash value of h of m, which will be equivalent to 1234. So when Bob matches with hash with the hash value and is generated, since the hash of message and encrypted value match, Bob can confirm that the message was not altered during transmission. So main purpose of digital signature is that message should not be altered or tampered in between the transmission. So this is how digital signature takes place, and how only intended user get to know that okay, the message has been received, the message has been sent from valid user, and in between the message is not tampered or altered. Okay, then you will understand the RSA algorithm, how it is most widely used asymmetric encryption algorithm, that is RSA, Ravist Shamir algorithm. So the first step here, to when encrypting any data, we have to first generate a key. I told you about how key generates are takes place, both private and public key. Let us see. So for that we need to understand the key generation function here. So we will consider two prime numbers here. Let us consider the prime numbers as small, so that mathematical calculation will be easier. So the prime numbers will be p equals to 2 and q equals to 7. So now let's another step is to calculate n, small n, which is multiplication of both prime numbers, that is 14 p into q. Then calculating the phi of n. This is a formula to calculate phi of n. You can see p minus 1 into q minus 1, which gives the 6. So to understand how this is calculated, the phi of n. So the phi of n is calculated of co-prime of 14. If we list down the 14 from 1 to, if we list down the numbers from 1 to 14, we can see we have to find the co-prime of n. So n is 14. So co-prime means that it must be not the factorial of the number. So we will eliminate the factors of 14. So 2, 4, 6, and 7, 8. So 10, 12. You can see on the right hand side these even numbers and the factors of 14 have been crossed. So the remaining numbers will be 1, 3, 5, 9, 11, 13. So number of values co-prime with 14 are 6. So after that, choose value of E for encryption such that the value of E should be greater than 1 and less than phi of n. So it must be between 1 and 6, and co-prime with n, that is 14, and phi of n, that is 6. So here we have taken the value 5, which is greater than 1 and less than phi of n, which is 6, and it is co-prime with phi of n and 6. Co-prime, if you know the prime factors, the prime factor will be 14 will be all cross number and co-prime will be non-cross number. So that is the number of count of numbers which is co-prime with that 14. So the E will be value 5 here. So to generate a key pair in RSA, we have pair as public key, which is E comma n. So for in public key, as we have E with us as 5 and n with us as 14. So for this we get our public key as E comma n 5 comma 14. So we need to choose a D for decryption such that, so D into E mod phi of n must equal to 1, and say that D equals to 11. So here we have to find the value of D, so that after multiplying the value of D with E mod phi n, it gives us 1. So how we list down the d here, how we have to guess the d here. So let's say again the factors of what e. So the factors of e are 5, 10, 15 and 20. So if I try to into, like say 5 into 5, that is d 5 and e as 5, 25, 25 mod of 6, that will be give me 5, 5 as a 25, 5 into 5, and it will be given not, it will be not equivalent to 1, that will not give us 1. So let us say we take a d as 11. So 11 into 5, that is 55. We mod the with, and we mod that value with 6, we will get the remainder as 1, which is 11 5 are 55. Okay, then after modding is 6, that is 6 5 are, sorry, 11 5 are 55, and the mod 6 will give the remainder as 1. Let's see, let us open the calculator to understand it better. So 11 into 5 gives us 55, and we mod that value with 6, it will give us 1. So we have to guess, choose the d in order, so that after multiplying with e and further mod with n 5 of n, it gives us remainder 1, or which should be equal to 1. So how we can guess the d? So we have to guess the d using the factorial factors of e here. So e will be used here. For example, factors of e will be 5, then 10, then 15. So if I use 10 here as d, so 10 into 5 is 50, and if I try to mod that value with 6, it gives a remainder 2. So we have to choose a d, it should give the remainder as 1. So this is how we have to select the d here. So for instance, the d is here 11. So the private key pair will be here d comma n. As we select d as 11, so the private key pair will be d comma n, that is 11 comma 14. So an encryption part here, if a and b are, a is sender and b is receiver, so this encryption will take place from a part, which using the public key of b, and the ciphertext is then converted to decrypt the ciphertext. We need private key, this 11 14. This is the key generation of receiver side, that is b. So this is the public key of receiver b and the private key of receiver b. Okay, moving further, now the encryption part. Now we have the keys here, private and public keys. Now moving to encryption part. So let us say a wants to send message hello, which is equivalent to, let's say, m, which is again equivalent to 2, for just to match the decryption, after to match the value after decryption, we are saying that okay, hello is equals to 2, which is equals to m. Now using b's public key, which is e equals to 5 and n equals to 14, we will encrypt the message. Now the formula to encrypt the message is c equals to m power e, that is mod m. So m is our 2 here, so let us see, c equals to 2 to the power 5, the e is here 5, and that is mod 14. So if you calculate this equation, you will get 32 mod 14, that is 2 raised to power 5 is 32 mod 14, that is equivalent to 4, equals to 4. So let's store that value d, the value 4 to, well, that's the variable d. So now in the equation part, the b will use here is private key to decrypt the ciphertext. Now what b has with him is his private key d and n 14. So to the decryption formula here is capital M. So capital M is our message, we have to find the message, so we are decrypting the message, and c is here 4. Okay, the Bob has received a c value also, it is ciphertext. So we have to decrypt the message. So let's start with using putting the values in formula. So that our message m should be equals to 4 to the power 11. So our mod 14. So 4 to the power, now this we have to, this you can calculate the value using calculator, or this is Euler's division algorithm, extended division algorithm. So we will dividing 4 is to power 11 into 4 into 4 is to power 10. Then again further we are making 4 into 4 to the power 2 into 5, that is 10 25. Then 4 into keeping the 4 to the power 2 in bracket and to the power 5. So 4, that is mod with 14. As you can see, 4 into 4 to the power 4 to 16, 16 to the power 5 mod 14. As 16 mod 14 is equivalent to 2, so we will be replacing that value 2. So 4 to the power 5, that is 16 mod 14 is 2 with mod 14. So if you mod 32, 32 mod 14 will give us 4, that is 2 to the power 5 is nothing but 32. So if you mod 32 with modding 32 with 14, it will give us 4, and 4 the 16, again 16 mod 14 gives us 2. Now if you see, we have got the message as m2, m equals to 2. Now at the encryption part we say, okay, hello, let's say a want to send message hello, that is equal to 2. So B uses his private key to generate that encrypted message, and found that okay, the message I have generated, the hash message I have generated is equivalent to the hash message received from A. So B successfully received the original message m equals to 2 here. Hope the concept is clear. So basically the main focus is here, the formula, decryption and encryption formula. Now mod n is functioning here as common value. Mod n is nothing but further if you're going to consider this as capital G, which is just curve on elliptical curve, just point on elliptical curve. So moving further, we need to understand the blockchain. What is blockchain network? How blockchain network is, what blockchain network is consisting of. So first of all, there are two kind of network. So there are centralized network and decentralized network. When I say centralized network, we can take the example of bank. As you see, the bank acts as centralized network here, whereas bank only has the information about the all account holders with them. Whereas in decentralized network, every entity in the network has copy of transaction on the network available to each and every node on the computer. So it is distributed ledger. Now what is ledger? Ledger is a transaction list. It is a collection of records of transactions, and it is shared with the complete decentralized network. Whereas in centralized network it is not shared, it is kept as a private and known to only one entity, that is bank. So this decentralized network on blockchain, which is blockchain, this cannot be altered. If we altered any transaction here, the rest of the entities nodes in the network need to know that okay, this transaction doesn't match with the inputted values, the transaction is not verifiable, so it cannot be altered, it is infeasible to alter the data. So integrity is equal to cryptographic hash functions, often paired with public key mechanism. So blockchain transaction has, it is advantages that blockchain transactions are fair, transparent, so that everyone in the network can see the sender, who is sender, and the receiver, which makes us to analyze the part, okay, this frequent payments are being made from one sender to another receiver, which is used to then capture an information and analyze the transaction. Okay, transaction is favoring this, the receiver A is favoring receiver B most of the time, so it can be tracked. So basic function, the basic structure of blockchain is its collection of blocks. Whenever you broadcast transaction to network, what is being broadcasted to the network, it is in the structure of block, you can imagine. For example, in block header part, we have hash of previous block, timestamp, announce is a random number is generated for each block, and it is unique to each block. The hash of block data. So this is the block data, and it has the hash of this block data and block data block. So you can see this is complete. It completes the block 1. So another block will be having the hash of this block. There's a block 1. As you can see, hash of block 1 timestamp. It's one timestamp. It's one mouse with the hash of block data, and the further block will have the hash of this data. For example, if I change anything in block 02, I try to alter the data here, transaction data here. Then after hashing the block data, and if block 03 and matching that block data with the hash of block 03 having the hash of block 02, it will not match as the transaction is being made previously verified. And if anyone tries to tamper the data in between the block data of block 2, the hash will not match. Further, it will verify that okay, the transaction is not valid, so it is not, it is untamperable. So the integrity is secured through this the cryptography has mentioned. So this is how the general structure of blockchain. Okay, now the drawback of blockchains is we know that everyone in the network can see the transaction moving from one side to another, like who is the sender and who is the receiver, and how much amount is being received by sender and received by receiver. So to address this privacy issue, the concept Monero has introduced that it's stealth address. There are three concepts Monero has, like ring city, ring signature, and stealth address. So ring city is used to hide the actual amount that is being sent over the network, over the transaction, and ring signature is used to hide the sender. And in stealth address, we try to hide the receiver here. So how this has been done, we will see this. So first, we need to understand what is why privacy in blockchain is crucial. So, as the privacy in blockchain can be as advantage, can also be as disadvantage. So, while transparency in blockchain ensures security and trust in the network, but it compromises the user privacy. If user doesn't want to represent its value and its sender, then it compromises its privacy. So, like for example, in Bitcoin and Ethereum, transaction details like sender, receiver, and amount are exposed to everyone. Anyone in the network can track and analyze the user activity. So, our key focus in privacy is that it should be untraceability and unlinkability. So, untraceability ensures that a transaction cannot be traced back to the sender, protecting its anonymity, while unlinkability ensures that transaction cannot be linked cannot be linked together to identity to identify common owner, maintaining the confidentiality of transaction history. So how blockchain these privacy features can be used is encryption and cryptography. Encryption includes secure transaction and protect sensitive information. Provide participant with cryptographic address instead of real world identities for increased privacy. So it doesn't actually expose the real world identities. It uses cryptographic address instead of real identities to increase privacy. And how we can implement is that there is the concept smart contract, which acts as consensus in the network. Like okay, we have to come at this consensus in the network that this will take place and this is how transaction will be transmitted or broadcast in the network. So smart contract acts as consensus between the transaction. So and incorporates privacy settings within the smart contracts to enable selective disclosure of information. So what different in stealth address we have, so that it is making the sender, it is making the receiver anonymous. So what extra we have in Monero's privacy model here? So the key components here we have is that first of all our purpose is clear. We have to ensure the receiver's privacy by creating one-time address for each transaction. So how it works? So here in Monero's privacy model, there are two additional keys being introduced to each end, like senders and receivers end. So the the overview of this how sender address works is that sender uses the receipt end public spell key. So first of all, we need to understand what additional two keys uh, are having with both ends. So as we know, in asymmetric key cryptography, there is private key and public key. Okay. So what Majora's steals address transaction model has introduced that every end, both the receiver and sender end, sender will have private view key, private spend key, public view key, and public spend key. Same keys receiver and receiver will have with him that private view key, private spend key, public view key, and public spend key. Okay, so these are additional keys with each end user. Okay, so the overview of this how it works is that sender will use recipients receiver's public key, public spend key, and public view key to generate one-time strength address. This will be raw one-time raw address, which is will be unique. The transition will be happen to this address. Now sender will use to generate this address. Sender will use his receiver's public spend key and public view key. Okay. So other is the stealth address hide the receiver actual address, preventing the others from linking translation to receiver. As we are using one-time raw address here, so it prevents linking translation to the sender, like who is sender and why it is remaining anonymous, how the sender is hidden here. Now we will see how this works. So the step one is the transition flow sending. It includes the from receiver point, okay, sender's point. So step one here is Alice will generate a random value and computes R. So first of all, Alice will generate a random value small r. Let us assume that r is 6. So she computes capital R. The capital R will be a point of publicly shared data. You can see we will see the later why we are computing the capital R. So to compute the capital R, we are multiplying small r with g. So let's say g equals to 10 and r equals to 60. Then r will be 60 because our small r is 6. So g is acting as phi of n here, and we can see in RSA there is one common value which is used to define key generation, which is used when encryption part is made. So that common value we have there is 14. So how that 14 is being utilized in key exchange algorithm. So that same value, same not same but kind of same value g, which is known as known point on elliptical curve. To understand this better, we need to deep dive into elliptical cryptography, how key exchanges, how this g is being picked up, and the g is universal here for your knowledge. The g is defined in the network and it is universal and constant. So the r will be our public part of shared secret. Further, we will generate shared secret that will help the mob, that is receiver, to identify the transaction that is intended for him. Like Alice is sending the transaction, so that he has to identify transaction of the transaction is being sent to him. So Alice includes R in transaction metadata. So this R will be public part of the transaction, which should be visible on blockchain to everyone. But the small r is only present with Alice. Okay. Now the second step here is Alice will compute a shared secret C. So this shared secret C is will have hash of small r into V. So what is V here? So V is public view key of Bob. So V is public view key of Bob. Let's assume small v equals to 5. So if we say small v equals to 5, then capital V will be V into G. Why V into G? So in asymmetric cryptography, public key is being generated. Yes, the public key is being generated from private key. So if we assume the private key as 5, that is small v, that's private view key. So it's 5, and as then for its public view key capital V, we will be multiplying its private v, so private view key small v into G. That is G is point on elliptic curve and it is constant to the network. Let us say G equals to 10. So multiplying 5 into 10 is equals to 50. So the public view key of Bob will be 50. Now what we are having here, small r, this is the part of Alice. Alice is generating shared secret here. So small r into capital V, that is 6 into 50. So the hash of, let's say, 300 is given as 12. So we have C here, which is shared secret key. We have capital R is equals to 60. Okay. So the next step is sending the transaction. Now the next step is now Alice has to create one time raw address of Bob, so that in network if anyone sees this transaction, sees the recipient address, then this transaction will not be traceable and linkable to the Bob by OVC. So let us say Alice create a one-time stealth address as K0 that will be formatted as C into G plus B. Now what is B? B is Bob's public spend key. So we have C here. You can see that is our C is equals to 12, which is nothing but a hash of small r into V. So hash of small r into V into G plus B, that will be 12 into 10 plus 70. Let us say public spend key of Bob is 70. Sorry, public view Bob's public view key, let's say, is B7. Here we have assume capital V as public view, Bob's public view key. So capital V plus B, Bob public spend key. So capital V we have. So for public spend key, ensure only Bob can later uses his private spend key B to spend the fund. So capital V is Bob's public view key and capital B is Bob's public spend key. So in order to get that, let us say Bob private spend key small b equals to 7. So to generate a public spend key, that is capital B, we will be multiplying that value with 7 into 10, that is 70. Please avoid this small b, it is not small b, it is small b. Okay, so small b, that is 7 into 10, and we consider 10 g equals to 10 here. So 7 into 10 is equals to 70. So after calculating this, let us say let's get the value as 190. Okay. So now tell that this is one time address. This is one time Bob address. Now what elements does the Bob we used to create this address? We have shared secret key C, which is wherein we have used Bob's public view key with Alice random R small r, and in addition to it we have add the public spend key. So after calculating, we get the stealth address as, let's say, 190. Okay, now what part of the creation, or like what part of the stealth will be broadcasted and will be visible on blockchain? So for example, if any attacker or hacker is present on the network, what he will able to see. Now Alice will broadcast the transaction. Okay, now what Alice will broadcast? Alice will broadcast capital R. Capital R is what? Small r into G. Because G is known to all network, but small r is not known to anyone other than Alice. So it doesn't make sense. Now, in order to get the capital R, everyone other than Bob has to go through a random value, calculate a random value till he matches the capital R. Just because Alice has small r with her. So this part is been public to everyone in the blockchain, and the amount and the destination key. Destination key is nothing but stealth address. So what stealth address is, what one can derive from stealth address? Like it doesn't have C to derive the stealth address. No one can link that value to any recipient on the network, as it is generated by Alice using Bob's values. So these two parts are being publicly visible on blockchain. So publicly visible part are basically Bob's public spend key and Bob wave key. So no one can use these two parts to link transaction to the Bob. Like how using capital R he will not able to generate a capital R using small r. Even if he try to generate a capital R, that doesn't make sense. He has to generate small r. He has to capture the small r so that he can trace the linkability between the sender and receiver. It's infeasible for anyone on the network to calculate the small r other than Bob. Bob itself is not calculating small r here. How Bob is decrypting this transaction, we'll see. So the flow you can see here of Alice will generate R, the computes capital R into R equals to small r into G. So it's to compute shared secret C. So it hashes the small r into V. V capital V is public spam key of pop. It creates a stealth address using that. So stealth address is nothing but C into G plus B. Okay, so C is nothing but the hash of RV into G plus B. So these are the stealth address. This is one time stealth address. That only we see this address in the transaction record. This is public transaction layer, and this is the part. This part will be publicized. This part is visible to everyone in the network. So transaction flow here, receiving part, how Bob will decrypt this transaction. How Bob will get to know, okay, this transaction is intended for me. So from Bob's side, the first step will be Bob has to compute a shared secret key. So Bob will use his private view key, that is small v, to compute C. Okay, but before that, he has to know, okay, transaction has been received on my side. How? So Bob wallet software will have algorithm to understand, okay, at 10:30 I have Bob wallet has scanned the all transaction that he has, and at least send the transaction at 10:35. So Bob wallet software will send the blockchain network at 10:40, and he will get to know, okay, at 10:35 I have received a transaction at my wallet, one time address at my wallet. So to understand that, okay, there is transaction on the network that might be intended for me. So to compute the shared secret now, to decryption part, he has to create a shared secret here. So whatever the part Alice perform here, like Alice generate a shared secret, he has to do the same part. Now what values he have with him from network is capital R, which is visible on network as we discussed, and small v as its Bob's private view key. So Bob will now compute shared secret, that is C dash, whereas Alice uses Bob's public view key to calculate shared secret C. Now Bob will use his private view key, small v into R. The R is public part of transaction, whereas Alice has generated R using its multiplication product of small r into G. So for example, let us say we have a hash of 5 into 60. So R is 60 here, you can remember. So we can calculate R equals to 60. So 5. So we have considered the Bob's private key as 5 before, I guess. Yes. So the Bob's private key is 5, and its public key will be 5 into 10 equals to 50. So 5 into 60 will be equivalent to hash of 300 equals to 12. So if you see what difference is here, when Alice calculate the shared secret C, that is 6 into 50. Okay, that is the generated value of R, capital R, small r, and into Bob's public view key. 6 into 50, that is 300. And how he is getting 300 here? That is 5 into 60. The 5 is private view key of Bob, and 60 is our shared secret. The using product of these two numbers, like capital R equals to 60 is available to Bob, whereas small r is not available. So capital R is nothing but the R into G. G is available to everyone on the network, but R is not available to everyone on the network. Okay, let's say Bob is not Bob, someone else, but only Bob has his private key, which is used, which whereas a Bob public view key is used to generate shared secret key. So only Bob will use his private view key to generate a shared secret key here. That is C hash. So let us say hash of 300 is given as 12. Now Bob has shared secret key here. This key, since to understand this better, the capital R is nothing but a small r into G, and capital V is nothing but a V into G. Therefore, small r into, we can derive this equation, V small r into R is nothing but the small v into R into G is nothing but R into V into G. It is R into V into capital R into capital V, that is Bob's public view key. So this relation is maintained here. So this gives the Bob same value that I used to compute the state address. Now again, Alice and Bob has his shared secret key with him. Now Bob need to calculate the state address. Okay, so that he will get to know this transaction is meant for me. Then he will be able to spend the transaction further. So Bob will calculate a potential state address value. So k dash 0. So he has shared secret key and C dash. It will be multiplied with G plus his public spend key. So that is Z0 key is 12, then into 10 plus 70. So what Alice did is here 12 into 10 plus 70. Alice did the same, and these are all variable values available to Bob as well. So 12 into 10 plus 70 is 190. If we match the stealth address Alice created for him for Bob and the Bob generated the potential chain value, it matches with the stealth Alice created stealth address. So capital H R into small v into capital R correspond to same value Alice used to create the stealth address. Correct. Now Bob public is capital B is Bob public when key that will prove the ownership of the address. Okay, so this is how Bob proves his ownership. Okay, so this so Bob proves his ownership that this transaction is meant for him. Now Bob matches the transaction since capital H hash of small r into v equals to hash of small r into small v into r. This part is matched. This part is calculated by Bob. This part is calculated by this. So when he matches the hash, the potential address matches the stealth address. Thus Bob confirm that stealth address matches Alice output on blockchain, meaning that transaction is for him. Now, in order to explain the transaction further, Bob has to sign the transaction. Now, Bob here can be both sender and receiver. The transaction, if you want to send the transaction further to someone else, then Bob will be sender, and if you want to deposit the transaction to his own account, then Bob will be a receiver. If Bob want to send someone else like Carol, then he will be generate a sale address for her. Same what Alice has done for Bob. And if Bob must generate new state address in both cases to ensure untraceability and uncryptability. Even if the Bob is receiver itself, like if Bob want to deposit amount to his wallet only, then he has to still generate a new state address for his wallet again to ensure untraceability and uncryptability. Though sending values to Bob doesn't make any untraceability here. What one we get to know that okay Bob has $1 million to Bob himself, but that means that only Bob knows where that comes from. So the spending part includes even if spending part include both generating one-time ephemeral private key T. So in order to spend the transaction, Bob have to generate capital small t, that will be one-time private key. So let us say we have shared secret C here and small b with us, that is Bob's public private spend key. So let us say it's a 7. I guess we have assume Bob public spend key somewhere. So capital B as Bob public spend key. So it is 70. G is our 10. So 70 divided by 10 will give us Bob's public private spend key. Small b is 7. So 12 plus 7 is nothing but a 90. So this is the first step in order to spend the transaction. Now he will generate our one-time private key. So here then again he will sign the transaction with that T. So he will sign the transaction, he will hash the transaction, he has K0 with him, stealth address with him, and message will be a transaction detail, and K0 stealth address, that is 90 and small t is 90. So let us say hash of K0 m into T is 20, and then capital S will be 380. Now he signed the transaction, he proves his ownership. Okay, this transaction is me, I am able to sign the transaction. Now further, in order to make sure, okay, I need to make my sender size as anonymous. He will construct a ring signature which will hide his sender's identity and prevent double spending. He uses ring signature is used to hide the sender's identity. How the working of ring signature is that here in Bob will create a ring signature, that is we will using public keys of public view keys of other decoy members on the network. He will create a ring network using that, and also he will be using his own public view key to sign the transaction by generating the decoy public keys. So verification will be done on the ring signature. Nodes on the network verify the ring signature if valid transaction is included in the block. So this part is been discussed already. So privacy implications of stealth addresses. What we are achieving through stealth address is that it reduces the linkability and targeting. No one in the network can link multiple transactions to the same entity. It makes them hard to establish patterns and associations. So this stealth address minimize the risk of targeted attacks such as phishing or social engineering. So other implication can be privacy preservation, whereas users retain full control over their privacy, ensuring their financial activities remain confidential and protected from unwanted surveillance. What are the use cases of any of this? Some of the use cases or benefits of stealth address will be anonymous transaction. The donors who want to remain anonymous on the network, that is idle for donations, then purchases or payroll while keeping identities private. Decentralized control, users manage their privacy independently without relying on intermediaries, enhance the security and reduce third-party risk. Then economic empowerment, the stealth address enable individuals to participate in global economy without revealing their identities. If they want to participate or they contribute on to global economy and they don't want to expose their identities, and stealth address are makes them unable to do that. Also, they protect their privacy, allows secure financial transaction, and helps more people access financial services. So these are benefits and use cases of